In this video, we will talk about finding the acceleration constraints for a double pulley example. So we're going to have the same strategy as before. We're going to find a constant length of string, and then we're going to write that in terms of the coordinate functions, the position functions of our masses with respect to the coordinate system, and then we'll take derivatives to get the acceleration constraint. So I've already done some work here for you. I've drawn the free body diagrams for these two masses. Notably, for mass M2, I have two tensions pulling it in this direction. Because if you can imagine M1 going in the downward direction, you would see, oh, well, that's going to pull this pulley this way. And then I have this tension also pulling my mass 2 in that direction. So we have two tensions. However, it's still all just one single rope as premised by the problem. And so we have our tension constraint that all the tensions are the same. I've also drawn a coordinate system for you because it's possible to do a global coordinate system here. We don't have any inclines or rotations or whatever. We just draw one. So here's one that's drawn already. And as you can see, the position functions have been written for our two masses as well. So this is the x position of mass 2, and this is the y position of mass 1 with respect to this coordinate system. With respect to this coordinate system, we can write out the F equals ma for our two masses. So for mass 1, we have really just the y direction that matters, so I'll ignore x. And in the y direction, we have, according to our coordinate system, up is the positive direction. So we have t1 minus m1g is equal to m1a. Then for m2, we have both x and y directions, but for the sake of this problem, I'm only interested in the x direction when discussing constraints with you all on this. So in the x direction, we see that to the right is positive and to the left is negative. Both tensions pull to the left. And so you get minus T2 minus T3. And that's it for the x direction is equal to M2A2. So let's just suppose then that there's T3 and there's T2 and there is T1. But it doesn't matter because they're all the same tension. And as a result, I'm just going to plug in that constraint right now so we don't have to think about it anymore. If you have minus t, it becomes minus 2t. All right, so now let's get the acceleration constraint. So to get the acceleration constraint, you do the same thing as before. We want the length of the rope in terms of the coordinate function. So the length of the rope from here down to here, well, as you can see, that's just going to be related to your y-coordinate. Your y-coordinate is negative, so it's going to be minus y1, and that'll be the length of your rope in that section. How about the length of the rope from here to here? Well, as you can see, that is going to be related to your x2. The way this diagram is drawn, incidentally, you see that it's drawn to the centers of the masses. So there's an extra constant distance being added in both cases. But as you know, when you take the time derivative of a constant, it's going to go away. So if you want, you can think of the length of the rope from here to here as being like, let's say that that's a constant c. The length of the rope is actually y1 minus c. Then you take the time derivative and that goes away. And then over here, the length of the rope, suppose that this is d. The length of the rope is going to be, and that'll get you the length of the rope in that section. So you take the time derivative, the constant goes away, and so there you go. Having that out of the way, we see that we get minus y1 for this length of the rope. We get positive x2 for that length of the rope. And then we get another positive x2 for the length of the rope there. And so you get plus 2 x2 of t. And then finally, you have the constant parts of your rope. So the part of the rope from here, the wall to here, that's always going to stay the same. The part of your rope that's going around the pulleys, that's always going to stay the same. Let's just call it all one big constant c. And likewise, in this constant c, we could put in the mini constants that we need to subtract out from our x and y coordinates, so we get actually the length of the rope. But okay, we have the length of our rope. We know it's going to be constant. Let's take two time derivatives of it as we usually do. Our first time derivative will make the length 0, and the c over here will also go to 0. And so we are left with minus a1 of t, because we took two time derivatives, plus 2a2, because we took two derivatives of x. So we got velocity and then acceleration. Well, we have our acceleration constraint then. Let's add a1 to the other side. And we see that a1 is equal to 2a2. a1 in the coordinate system for m1 is equal to 2a2 in the coordinate system for m2. All right, so we can write our constraint as we've done before. They're the same magnitude, but multiplied by 2, same direction as well in their coordinate systems. So we get a1, we can write that as a, and a2, we can write that as 2a. We then plug in, and we get t minus m1g is equal to m1a. And then over here, we get minus 2t is equal to m2 2a, or in other words, minus 2t is equal to 2 m2a. And then from there, you can proceed to solve your problem, solve for tensions and accelerations as you desire. But that's how you get the acceleration constraint, so you can solve the problem using Newton's second law.